Hey everybody, this is Mr. Piercy, and what we're going to be looking at in this video is this is piggybacking off of things that we've done with integration with partial fractions or long division. And in this case, we're going to be looking at a challenge problem where we're going to be trying to do partial fraction division using U substitution. So let's go ahead and jump into working out this particular problem. And starting off with, oops, I did not mean to do that. Let's go ahead and get a color here and get to work. So we have the expression sine of x over cosine of x times cosine x plus 1. And we can use U substitution here because if you notice the derivative of cosine is sine, so we can work with that here, or rather it's the negative sine of x, but we're going to be doing some U substitution, so I'm going to say U, oops, and it's wanting to do it all dotted like, okay, so there we go, let's do U. Let's say U is equal to the cosine of x. So that means du will be equal to negative sine of x times dx. Now what this is going to allow us to do for our problem is we're going to be able to rewrite this in U notation, where I'm going to say the integration, where indefinite integration, is going to be a negative 1. The negative 1 comes from the negative sine of x uh, over u times u plus 1 du. So what we're going to do now is we're going to be able to use the partial fractions. And some of you may have been wondering, well, why didn't you take the negative sign out? Because this du material that we have here doesn't match this du stuff that we would have here. And that's because the negative sign, whether it's inside or outside in this case, really isn't going to play a big role in simplifying the expression. So that's why I'm not taking the constant out. So going back to the problem, at this point here, this is where we're going to do our partial fraction integration, and I can't draw an arrow apparently. At this point here, oh, this is where we're going to be doing, and I can't spell either apparently, partial fractions. Partial fractions. Okay, so we're going to have a break this up where we have a, the integration of a. Let me give myself a little bit. Should have given myself a little bit of space there. Over u du plus the integration with b over u plus 1. And this is where we kind of, again, take the denominator and find its solution. So let's find the value of a. So a's denominator is just u. So I just set u is equal to 0. And we can use the numerator, which is negative 1, over the b denominator, which would be in this case 0 plus 1. And so the a value, negative 1 over 1, is just going to be a negative 1. So that negative 1 is going to go in here for a. And now let's go ahead and do b in a different color. So let's do b. I'm going to give go to the right here. I have a little bit more space. So b's denominator, if I set that equal to 0, that's going to give me u to be equal to a negative 1. So now I'm going to take the negative 1 in the numerator over the, the denominator of a is just u, so I substitute the negative 1 there. Negative 1 over negative 1 simplifies to be a positive 1, and that is what I plug in for b when I do my partial fractions. Let me give myself a little bit more space now. So going back to my original color that I was working the problem out in, we're going to have the integration. In this case, a is going to be replaced with a negative 1 over u du d, no, where aren't you writing? Du plus the integration. Oh, and it's not wanting to write again. I don't know why it's doing that. The integration of b, so b gets replaced with a positive 1 over u plus 1 du. And at this point, we can do our integration. So the antiderivative of the first fraction, negative 1 over u, will be negative 1 times the natural log of u. And the next one, the ratio will simplify to be 1 times the natural log of u plus 1. And we have a constant that we're adding because of the indefinite integration. And now we can, now that we've integrated the function, we can substitute our u values back in. So u, we said, was the cosine of x. So here I'm going to say negative natural log times the cosine of x plus the natural log of cosine of x plus 1 plus our constant. And if we really wanted to, we could use properties of logarithms to condense that a little bit, but I don't see the need to do so. So that is U substitution with our partial fraction integration. And we'll kind of do the same thing on this example. So if you feel confident enough in what we did in the last example, I encourage you to go ahead and pause the video and try and work this one out ahead of me. But presuming that you've paused the video and done your work, let's go ahead and try working this particular example out. What I'm going to say here for you in this example is I'm going to say, and just give me 1 second here because I forgot something I need on my side of the camera. Let me clean this up a little bit here. I have u. I want u to be equal to the e to the x power. So that means du, in this case, will be e to the x power times dx. So let's take a look at what that's going to do when we do our U substitution. So changing the given integrand, we're going to have U, or rather e to the x dx. That's going to be du, so that's just 1 du. So I have 1 over, and the denominator e to the 2x power. Well, everything is going to, we're going to change it from e to the 2x power from u squared minus 1, and we have to multiply it by du. So now this is where we are going to do our partial fractions. The denominator is factorable as the difference of two squares. So I'm going to get a over a u plus 1 du plus b over a u minus 1 du. And from here, hopefully you've seen enough of the examples with the partial fraction to see how this is going to go. So let's go ahead and do, there we go. Let's do a in red. So if I set a's denominator equal to 0, I'm going to get u to be equal to a -1. So the overall numerator of the fraction is just 1, so I'm going to say 1 over, and I'm going to look at the denominator that's under b, substitute the 1 there, or the -1 there, and that'll give me -1 minus 1. So that'll give me -1 over 2. That's going to be the value that I plug in here for a. And now we're going to do the same thing for b. I'll do that in a different color here. Let's try this green. So b, when I do that, setting b's denominator equal to 0, that'll give me u is equal to a +1. And so that'll be 1 over 1 plus 1 when I substitute u into the denominator under a, and that will simplify to be a +1 over 2. And so that will be the number that I put here for b. Now going back to my original blue color here, we're going to get the integral of -1/2 over u plus 1 plus, oh, and I forgot my du here, du plus the integral, and b is a +1/2 over u minus 1 du. And if you want to, you can pull out the fractions if you would like as constants, but it's really not going to change the value when we take the antiderivative here. So that's what we're going to do. Let's go ahead and take the antiderivative of both sides, on both sides of both integrals that I have here. So the ratio, the fraction on the left will give me -1/2 multiplied to the natural log of u plus 1. And then the next one will be follow suit, and it'll be 1/2 times the natural log of u minus 1. And because we're doing indefinite integration, oops, we're going to say plus c for a constant. And now that we are at this point, we've done our integration, now we can substitute our u term back into the problem. So that'll give us -1/2 times the natural log of e to the x power plus 1 plus 1/2 times natural log of e to the x power minus 1 plus c. And again, if we really wanted to, we could condense that with properties of logarithms, but I'm not going to do that at this time. Hopefully this is going to give you enough in your math toolkit to work any kind of partial fraction problem or long division problem. Partial fractions can be a little bit tricky because there's several approaches that you could kind of take with them, but long division or synthetic division, much more student friendly, much easier to pick up on. But that's going to wrap it up for this video, guys. Thanks for watching and take care.